Okay, hi everyone. Sorry for the garbage can. But thanks for being flexible this week. I have a big presentation in about a month, so I have a couple things I need to do. So if I'm a little MIA, I'm just probably not sleeping. But this will be probably the only time that I have to change the schedule. We're just working with some of the people that have to take the makeup exam too, so I have to get your grades and everything. So I just had a couple of scheduling things this week. But anyways, how we feel about this next topic that we're talking about. Okay-ish. What do we want to see today? Is it more like practice with the new stuff? Do we want to like kind of talk through it a little bit? What are we thinking? Talk through it a little bit. Yeah. Is it mostly like the capital K and the equilibrium and everything? Yes. Okay. So when we talk about equilibrium, right, it's always going to be denoted as a chemical reaction with the forward reaction and the reverse reaction. So, right, A plus B are your reactants here, going to C plus D, which are your products, right? That's going from left to right. But when we have equilibrium, that means that the reverse reaction is also happening in equal and opposite manner. This is probably the time of the semester you're going to start hearing me say equal and opposite a lot, right? Exothermic and endothermic are equal and opposite if you're talking about the reaction. If the forward reaction is exothermic, it's equal and opposite endothermic in the reverse reaction. Okay, so this way is the forward, but the reverse is also happening. Okay, so you could also write this as C plus D is going to A plus B. Right here, your products now become your reactants, but and then your reactants become your products, right? You can think of it either way. Whenever you see those double arrows, you can always think of it that way. There's a lot that goes into his notes about kind of using that extent of the reaction, right? That X value that we talked about. But what it boils down to is that we have an equilibrium constant that's going to tell us if our reaction is product favored or reactant favored. Does anyone know how we set up K? Good, right? So we have products over reactants, and specifically going to be the concentrations. That we use in this expression. Okay, so how would we write the K for A plus B goes to C plus D? What goes on top? Mm-hmm. And what goes on the bottom? Concentration of A, concentration of B. Perfect. Okay. Right, always products over reactants. If we were talking about the C plus D goes to A plus B, we can write that as K is equal to A plus, or concentration of A times concentration of B over concentration of C times the concentration of D, right? You can write it for the forward and reverse reaction. We can tell that purple K and blue K are inverses of each other, right? If we took purple K to the -1 power, we would get blue K. Right, we can say purple K -1, we end up with blue K. Right, that'll be helpful later on. Probably like Monday or Tuesday, or Monday or Wednesday next week. Okay, what goes into K? What types of things can go into K in terms of its state? Yeah. Good, right? So gas and aqueous phases. can go in K. What cannot go into K? Yep, solids cannot go into K. Anything else? Can liquids go into K? So liquids also do not go into K. Okay, when we think about it, something being aqueous, we're talking about the thing being dissolved. So if we talk about sodium chloride, right, that's going to be aqueous in solution. And we're not talking about the water that it's aqueous in. We're talking about the actual sodium or the actual chloride and the concentration of that. Okay, so solids and liquids do not go into K, but your gas and your aqueous solutions can go into K. If we talk about just regular K in general, right? We talk about there can be KEQ, which is just equilibrium. That can be broken up into a plethora of things, right? We could talk about KC or KP. Most of the time, your KC is going to be what you're going to be working in. We mostly work in concentrations rather than pressures, but your KP is just going to be partial pressures. Of gases. Okay, and that's going to look very similar to products over reaction. Products over reactants is just going to be your pressure of your products over the pressure of your reactants. You consider your pressure as the concentration that you're talking about. Any questions on the difference between KC and KP? Feel okay? Feel solid with this? Okay. Let's do a little practice. Okay, let's try these three. Everyone can read that. Okay, do you want to try and do this together? Or you want to give a couple minutes to work on it on your own? Are we okay working on our? Okay.
relatively easy type of question.
Say it again.
It's a relatively easy type of question. It's not something that is like.
Yeah, this is just getting you practice with it.
Yeah. Because I'm just like, so much to remember from the lecture, just like wrote it all down, and I feel like this seems really easy. I hope I didn't like over the science.
You work a lot with K moving forward. You'll talk about KA, KB, PKA, and all this stuff. KSP. So this is it's just important to know how to write them now because you'll be doing a lot of them. Okay, did we get an answer for A?
Yes.
Okay, what did we get for A?
Is equal to concentration of C to the third power over concentration of A squared times concentration of B squared.
It'll just be B, but yes.
Oh. Yeah.
Yep. Yep. Okay, awesome. So we didn't talk about this before I introduced it. But when you're talking about K, when you're given a chemical equation, as long as it's balanced, then you can use the coefficients in front of your reactant or product as the exponent. So here 2A means that we have a stoichiometric coefficient of 2. So that means that in your expression, the concentration of A will be squared because for every 1 mole that B changes, A will be changing by 2. So your concentration will be off by a factor of 2. Okay, any questions? Yeah.
I just have a question about like this on the exam. Like, do you think you give us an unbalanced equation and then ask for K, but like not specifically state that we need to balance it?
I have not looked at the homework yet, so I don't know if that's like, yeah. So but I feel like he gives the vibe where he could. Yeah. Which is why I gave you C. I have always told my students to always check your equations to make sure that they're balanced before you start using anything, because that'll change your factor of X, and that'll change obviously how you solve for X in many ways. Especially with K, like you take this factor, if it's a coefficient of 2 or 3, it carries with you throughout multiple steps throughout K. So you want to make sure that it's balanced before you start it, because if you don't have it balanced and you start solving for X, it'll be a nightmare to try and fix again. So give yourself an extra minute to make sure it's balanced before you have to go back and give yourself 5 minutes to fix your mistake. Okay, so for question or letter B, what K do we have? What's on top? Awesome, right? Those are not going to be squared. So HI has a coefficient of 2 in front, so that's going to be to the power of 2. But H2 and I2, even though they're diatomic, that's just staying as a diatomic molecule. Okay, and then so we brought up the question about having to balance an equation, so that where C comes in. Is C a balanced equation? It is not. How are we going to balance this? Oh, sorry. Did you say H2? Yep. I'm sorry. 3. Perfect. Yep. Yep. So we have 2 nitrogens to start off. There's only 1 in our ammonia. So we need a 2 in front of that nitrogen. That makes 6 hydrogens. And so we need a 3 in front of our H2 in order to make that 6 hydrogens on our reactants. Okay, so if we have now 1 nitrogen plus 3 hydrogens goes to 2 ammonia molecules, what is our K?
The K is equal to, oh, it wasn't balanced?
No.
Oh, well, it's equal to NH3 raised to the second power over N2 not raised to any power other than 1, and H2 raised to the cube.
Perfect. Yep. Okay, so this be your first lesson. Make sure that your reaction is balanced before we start using it. All right, any questions on just writing K? And now all of these have one product and two reactants, but you could always have more than one reactant. You can have more than one product. You can have one reactant that is splitting into products, because if we do the reverse for any of these, right, we can say that in the same sense, 3C is going to 2A plus B, 2HI is going to H2 plus I2, and then your 2 ammonia is going to nitrogen and hydrogen, right? So you could write the opposite for all of these. Feel good? So the opposite is just going to be like the inverse. So if we were to do C, yep, it would be, I tend to write these in the, right, if you're doing the opposite, you're going products to reactants, I flip them. So then I see that it is reactants to products. And then K is just N2, 3H2, oh, sorry. Yep. For me, it's visual to be able to write it down, reactants to products, then I can put products over reactants. Pretty good about seeing it in reverse, the way that it is in the paper. I'm jealous. Yep, so it's just K to the -1. Yeah, so you'll say that like this would be K and this would be K -1. Or I think they put it as a subscript, so it's K -1. Any other questions about inverses of Ks?
How does it all time affect activities? That is in those types of problems not relevant.
Yep.
But in like the I haven't managed to read the chapter yet.
So if we have a practice questions, we could say that we have, we'll take this one. Right, we just found the K for this a second ago. Right, so the whole process or the whole point of equilibrium is that you're going to start off with your reactants, right? You'll have some concentration of reactants and you'll have no concentration of products, right? So we could say we have 1 molar of this and 1 molar of that and 0 molars of your product. So if we have all reactants and no products, which way is our reaction most likely going to proceed? It's most likely going to go to the products, right? We're going to form some product when we mix your hydrogen and your iodine. Okay, so if we're making product, what does that do to our reactant? It'll decrease, yep, it'll decrease the reaction, right? We just talked about rates of reaction. If we start off with something high as our reactant, we saw that decrease depending on the order of the reaction, right? Order of reaction here does not matter. It really just matters that reactant is being used up in forming product. Okay, so at some point, we don't know what this is, but we'll have some factor of X that's decreasing, and that's the activity, right? What is I2 going to decrease by?
Decrease by a factor of -1.
Yep, also by that factor of -X, right? There's no stoichiometric coefficient in front of H2 or I2, so it's just considered one activity or one X that is being decreased by. How much is I or HI going to increase by? It'll increase by 2X. Right, that coefficient is going to drop down with the activity or with that X factor. Because for every 1 mole of H2, we get 2 moles of HI. For every 1 moles of I2, we get 2 moles of HI. Okay, so at equilibrium, this is where this ice table you might have heard of comes from. We have our change in our equilibrium. So at equilibrium, we'll have 1 molar minus X, 1 molar minus X, and then 2X as our concentrations at equilibrium. Okay. Right now, all you know is that, right, you might be given the product concentration, and then you can find how much is being decreased by. But the principle behind it is that your reactants will decrease and your products will increase. Does that make sense? How, yeah, change.
Activities are just like the concept of the actual like chemical reaction,
Yep,
rather
it's,
than just like how much we had of them.
yeah, so the activity is just how much it's changing by, like how much is it reacting, and how much it's reacting by is how much it's changing by.
So if we have like some reaction remaining, it might change, have a different activity than like the stoichiometry.
You will most likely have reactants remaining, but that's taking into account the activity already.
So it's just like a weird concept to me, like the activity. So is it just like to be? I remember Dr. Lindau saying that like concentration was like invented, but like activities were like not. But
Yeah, it's a weird concept to grasp if you can think of it as more of like the reaction happening is the activity. And so the reaction happening, it might not go to completion, right? You might not use up all of your reactants. You might have some left over. And that's where that you can find that equilibrium concentration of everything, because not everything is going to turn into products. And if everything does turn into products, it'll either not go back to reactants, or some products will go back to reactants, and you'll have both at equilibrium. Does that help a little bit?
yes.
Okay. Alrighty. Any other questions on the ice table? He kind of walks you through this step in your notes, without necessarily using initial change in equilibrium. But that's what ice stands for. Okay, so we could have a practice question. Okay, so we have calculate the equilibrium constant Kc for the following. And we have 2HI goes to H2 plus I2. And we're given equilibrium concentrations. Do we want to try this? Walk through it? Are y'all okay to try it? Yeah, okay. Give it a try. Think about what we just talked about of what it means to have an equilibrium concentration. How that plays into what you would plug into K. Alrighty, did we get a K value?
Yeah.
What did we get for K?
0.0163164. So about 0.0166.
That's what the correct sig figs as well, to 3.
Yes.
Okay, and someone want to tell me how they solved this?
Now, first taking the concentration of hydrogen and iodine, and multiplying those two together, and then dividing by its quantity by the concentration of which I would be hydroiodic acid squared.
So, right, we have our K value here is, right, different from what we just did. It's the inverse of what we talked about earlier. So this would be H2 times I2 over HI squared. And then we can plug in the equilibrium values that we know. So this would be that, and then K equals 0.0166. KC is for your equilibrium of concentrations. KP is for your equilibrium of gases and their partial pressures. Yep. But you can use a gas and a KC too. It's just if you're given partial pressures, yeah. Yep, if you're given partial pressures, then you would want to use KP. Okay, any questions on K here? I have a question. Is this reactant favored or product favored? Say it again.
Product.
Okay, why would it be product? Okay, I like your thought. Anyone have a different answer? Nope. So the value of K will tell us if it's product or reactant favored. K has a couple of options. K can equal 1. K can be less than 1. K can be greater than 1. K can be equal to infinity. And K can be equal to undefined. If K is equal to 1, what does that mean about our products and reactants? Yep, they're equal. Here, products and reactants are equal. I'm sorry, this is not undefined. This is. If K is less than 1, which is going to be more favored, your numerator or your denominator? Denominator is going to be more favored. And what's on the denominator? Your reactants or products? Your reactants are on the denominator. So that means that if it's less than 1, it'll be reactant favored. And by favored, that means that there are just more concentrations of reactants at equilibrium over products. What if it's greater than 1? Right, product favored. What about if it's infinity? What does that mean?
Means it doesn't end.
Right, it doesn't end. So if we have a really high number on top, right, then it's going to be infinity. And if it's really, really high on top, that means that we have a non-reversible reaction. So this is all products.
When you said that technically it's like to find out if a reaction is like at equilibrium, we just have to wait forever. So literally just because we can't be really, really, really sure that it won't like change slightly unless you would wait forever.
Yes. Yep. But
We are very confident.
yeah, we're very confident it's not going to change. Yep. As long as temperature stays the same and everything, we're pretty confident it's not going to change. Cannot make reactants. Right. If it's infinity, that means we have a very high numerator, which means we have all products and no reactants. So it's an irreversible reaction, was the word I was looking for. And then if K is 0, what do we have? We have the opposite, right? We have no product, we have only reactants. So here we have no reaction at all. Right? Nothing is happening for us to form any products. We just have reactions sitting there. And then that means that at equilibrium, no products are being formed. And so we either need to increase that temperature, make our molecules closer together, something like that. Most likely increase temperature. Okay, so going back to our question is HI splitting up into its H2 and I2, is that product or reactant favored? It is reactant favored. It likes to stay as HI. So if the reverse reaction, if we're forming HI, is that going to be product or reactant favored? It'll be product favored, right? Where it's still favoring that HI being formed. It doesn't really have. It's possible, yes. If you're in the range of 0.001 to 100, then you have very similar equal parts reactant products. It's when you get above 100 and into like scientific notation of K, where you have like very strongly reactant favored or very strongly product favored reactants. Yep. So you can say, right, we say K is equal to 1 is product and reactant favored. It's more of a range of 0.001 to 100. Or is it be 0.01? Whatever. It's about that. Yep. Yep, the K is equal to 1 is more like a range of 100th and 100.
So like less than would be like less than 10.
Yeah, with the, so less than 1 is more actually like 1 times 10 to negative 3. That's when it's like, okay, reactant favored, or 4.6 times 10 to negative 12, right? That's going to be reactant favored. Where if it's greater than 1, then it's like, 5,000 or 1.6 times 10 to the 7th, right? Those are product favored. Any questions on what I mean by like reactant and product favored in the ranges and stuff? Okay. Okay, so then let's do another one.
Most like reactions in reality, like equilibrium reactions, like,
Yep. Almost everything is in an equilibrium.
so we almost never have something that like stops.
Yes. Sorry, this is not CO2, it's just CO. Okay, so we have carbon monoxide and hydrogen gas form something that I'm supposed to know. Methanol. And a reaction starts off with a concentration of the carbon monoxide and a concentration of hydrogen. At equilibrium, the concentration of methanol is another value. And I want to know what the K value is. Do you want to try this? Do we want to work through it together? Try it? Yeah? Okay. I'll give you a couple minutes to try it. Right, it should tie in what we just did, and then like the two most recent things we talked about. If you're stuck, I suggest writing a table. we have an idea of how to start this? What are we thinking first?
Other problems,
Say that again.
like the other problems, it is moving a different way. Okay.
So it's important to know what we're starting with and what we're like, it's important to identify what we're given. So we are given initial concentrations of our reactants and we're given an equilibrium concentration of our product. So can we just plug in the values given to K? No, we can't, right? Because if we were to fill out a ice table, right, we could say, I tend to form these by saying my reaction again. And then I just make a chart like this. Okay, and then you can fill in what you know. So we know that we have those values there. Does that look correct? Okay. So what else can we fill in from this chart? What do we know is our initial concentration for methanol, that CH3OH? It would be 0, right? We're not given initial concentration. If we're not given one, we can assume that it's 0. What is that change going to be for the CH3OH? I like plus, just plus X, right? We only have a coefficient of 1 in front of that CH3OH, and so it's just 1X that it's changing by. So can anyone tell me what X is? Yep, it'll equal whatever this concentration of that methanol is. Okay. So what about the change for CO2 and for CO and H2? What's going to be the changes in terms of X for these? What about CO? Minus X. What about H2? Minus 2X. Yep. Okay, so at equilibrium, we'll have and then the concentration of our methanol. We already know what X is because it is just the change of that methanol concentration. So you can solve for the actual equilibrium concentrations and then plug that into K. So, right, equilibrium here would be 0.18398 minus that. This is 0.4. This is going to be so it's going to be minus 2X. And then we can plug all of that into K. And K is going to be CH3OH over CO times H2 squared. Did someone get a value for K? My notes. Yep. I have 28.6, so very similar. Any questions on how we're going to do that one? Yes, the X is what it's changing by, and it's the concentration that it's changing by. Yep, so we could solve for X because we could say, right, this is like concentration here. Yep. So if we wanted to solve for it, we know that our final minus initial, right, is going to be, is equal to equilibrium. So our final was 0 point, or sorry, our final is X minus 0 is equal to this. And so X is equal. Yep. Right, if that was changing by plus 2x, then it would be 2 divided by the equilibrium concentration. Okay, and there will be times where you don't know what the equilibrium concentration is of that product. And then you have to solve for X by plugging it into K, and you'll be given a K value. But y'all have not talked about that yet, so. Feeling better about K? Yes, okay. So I guess if we want to try and think like Dr. Lindahl, see what kind of questions he might ask on his exam. You are most likely going to be working in concentration. What units of concentration is that? Yep, we usually work in molarity. What does molarity break down into?
Moles per liter.
Mhm.
So you can be liters.
Yep, we have moles per liter. So what could we be given in order to get to moles per liter?
Gas stuff.
So we could be given moles of products and the volume of the container that it is performed in. Right, so here that's a little bit straightforward because we have moles of our reactants or products in the container. So if you have 1 mole in 2 liters, right, then your molarity is going to be 0.5 because it's moles over liters. What else can we do with moles though? What can we change that into?
Oh, grams.
We could change it into grams, right? We could be given grams of reactants or products. Right, then we can use the molar mass to get to moles, and then you would also be given the volume of the container. And it would be, I think, maybe a little bit too hard. But you could be given pressures and temperature of reaction. And through PV is equal to nRT, you can arrange this to N over V, which is moles over liters. It's equal to P over RT. And you could use the pressure that you're given and then the temperature of the reaction to find moles over volume. And then you can use that as your concentration. And that's how you actually relate KC to KP is through Pivner. Any questions on what we could be given? And that's like if you're in that you could be given reactants or products, you could be given initial concentrations or equilibrium concentrations. The best thing for you to do is, I think, to form that ICE table and kind of fill in what you know and what you don't know. and see if you can find and solve for X. Yes.
You would never like just be given an initial without like an X. Because
Um,
how would you find out X if you don't know like any of these?
Yes, so, I can kind of show you how to do that. We won't solve one because I don't think you've talked about it yet, but we could be given something. I'll just do like generic, right? We could have 2A plus B goes to 3C. We could be given that K is equal to 55. And then we can say that, A initial is 0.5 and then B initial is 0.5. Then we want to know the concentration of C at equilibrium. Okay. So if we solve this like we just did the last one, right, we're going to rewrite our ice table. So we have 2A plus B goes to 3C. Okay, what do we initially know? Yep, we know concentrations of A and B. What do we know for C? Nothing, right? Do we know any equilibrium concentrations? Nope. We don't know any, right? Do we know how our reaction is going to change by? Yes, we do, right? What is A going to change by? Minus 2x. What about B? Minus x. What about C? Plus 3x. So at equilibrium, what are our concentrations? What is it for A? Yep, 0.5 minus 2x. B is going to be 0.5 minus x. And then C is going to be 3x. We're given that K is 55. So if we were to write the K expression for this, we would say K is equal to, what's on top? C cubed over A squared times B. What do we put in for concentrations? Initial change or equilibrium? Equilibrium. Do we know what our equilibrium concentrations are? Ish, right? We have stand-in values for them. So we could say that K is 3x, because you need to include that 3x, to the third over 0.5 minus 2x squared times 0.5 minus x. Okay, we don't need to actually solve this, right? Because then you can say that K is equal to 55. You don't actually need to solve this because this involves foiling and then foiling your foiling and a cube root, right? So it's a lot of math, a lot of algebra. But that's how it would be more complicated or more simplified than this, probably just an x and an x squared of some sort. But that's how you would solve it if you don't know equilibrium concentrations. You'd be given a K. Yep. Does that make sense how we set that up and what we plugged in? Yes. I just was briefly looking through your homework while you're working on the last question. And so I think there are a couple of examples of this so you can practice with it. Any other questions on K? Are we feeling okay? Great. Alrighty, well, it is almost 6 o'clock. There's no more questions. I'll let you go. If there's any other questions, please feel free to ask them. In terms of your grades, they should be up tomorrow. I will try to be faster with the next one. I have to talk to Dr. Lindahl about makeup exams and stuff. But should be out tomorrow.
Considering we have the key.
Yeah, you have the key, so you can kind of know what your answer is, but you can see if you get an A, B, C, or D tomorrow.
Oh, there's distribution.
Yeah, yep. Yes, so we curve it based, right? We do the bell curve, and he has like a distribution of people that get A's, distribution of people that get B's. So this will all go towards your 750 total points for this exam or for this class. So then so it pretty much just comes at the very end, right? We're going to bell curve all of them, and then so at the very end we kind of look at all the distributions of A's, B's, C's, and D's, and then bell curve that.
So it's the bell curve based on.
Kind of, yeah.
Oh,
Yep.
I thought it was the bell curve based on.
Yeah, so it'll be like it's a curve of a curve, because right, you can total all your points. You can kind of think of where you are based off of the curve of each exam, right? Like if you have an A every single exam, then you can expect probably an A, right? If you have 3 A's and 4 B's, then you can expect a B, but he might bump it up so that like one of your B's is now an A, right? And you can get an A. So that's where you can kind of think of that, start like averaging your A's and B's to see if you're leaning more towards one or the other.
And then normalized to 90, that means that like because the one question of like take more.
Yes.
Does it mean that 90 is now the highest?
Yes. So for the A version,
points,
yep, you can have a max of 90 points. Yep.
not the percentage.
Yes.
but
Yep.
points.
Yes, it's of the points. So we normalized it to 100. So if you had an 80 out of 90, right, then you have that times 100, and that's how many points you got.
Yeah.
Yes.
Luckily, the question that was taken off was one of the only big one I missed.
That one, there was just no close answer, so we couldn't accept it. Yep, thank you.
At least this class is going good.
That's good.
With the exception of the lab, which is just stressful. And I had a physics, like engineering lab. That was on Monday, and I had the lab for this class on Tuesday, and I